All right, guys, so we had done the first 4 examples last time. We finished with example 4, which was talking about how to graph our rational function. So we have a few more examples with graphing that we need to look at. And let's see, so this was the last example we did. So our next one is number 5 here. X divided by x minus 2, the quantity squared. So remember, we start by finding our asymptotes first. So if you're trying to find the vertical asymptote, remember this is where we take our denominator, set it equal to 0. So f of x equals x divided by x minus 2 squared. Let's start with the vertical asymptote. So take the denominator, set it equal to 0, and what's the first thing we should do here? To try and isolate our x. Yeah, take a square root on both sides to get rid of that square. So the square and square root will cancel each other out, leaving us behind with x minus 2. Of course, again, 0 does not take a positive or a negative sign, so it will become just 0, which of course that means we are going to have x equals 2 as our vertical asymptote. Okay, once we do the vertical one, now we have to decide, will we have a horizontal asymptote or an oblique asymptote? And how do we know which is which one will have? So remember, it depends on the degree of your x value. If the degree of the x is less in the numerator than the degree of the denominator, you're going to have a horizontal asymptote. The only time we have an oblique asymptote is when the degree of the x value in the numerator is larger than the degree of the x value in the denominator, which is of course not the case in here. So for this example, the horizontal asymptote we have x over x minus 2 squared. Now if you want to make it easier, you can go ahead and multiply your denominator. Go ahead and FOIL that, which will end up giving us x squared, that's minus 2x minus 2x, which will become negative 4x. Negative 2 times negative 2 will make it positive 4. So go ahead and FOIL your denominator if that helps. And then remember what we talked about when you're trying to find your horizontal asymptotes. You take the largest degree of your x value and divide each term by that highest degree. So in this case, of course, our x squared is the highest degree. So we take our x term on the numerator divided by x squared. Then we've got x squared divided by x squared minus 4x divided by x squared and plus 4 divided by x squared. So you take each term and divide it by the highest degree of your x value. So for the numerator, one of the x's will cancel out, leaving us behind with 1 over x. And as x is going to infinity, where is the value of our fraction going?
Zero.
It is going to 0. Remember how last time we have taken the 500 and divided it by large denominators, 999, 9099, and all of those. So anytime I have a constant or a smaller value in the numerator and a larger value, or basically an x in the denominator, as x gets really large, my fraction will get really, really small. So x over x squared or 1 over x will start going towards 0. And that's the same thing that's going to happen over here with 4 over x squared, this last term on the bottom. He is also going to 0. For that matter, our middle term, one of the x's will again cancel out, leaving us behind with 4 over x. And this 4 over x will also go to 0, which means this guy is going to 0. X squared divided by x squared, of course, comes out to be 1. So you actually end up getting 0 over, honestly, you have 1 minus 0 plus 0, which is 0 over 1, which is 0, right? So basically, our horizontal asymptote is going to be at y equals 0, which also happens to be our x-axis. Now you can use this whole process for finding out what your horizontal asymptote is, or you can remember, and we had talked about this last time again, anytime the degree of the numerator is smaller than the degree of the denominator, x-axis or y equals 0 is always going to be your horizontal asymptote. If they are the same degree, so if I had x over x, which this guy is of course x over x squared, but if they have the same degree on the numerator and denominator, then it's the ratio of the leading coefficient. So that would be your horizontal asymptote. So those are the two different cases you need to remember when you're working with horizontal asymptotes. Okay, so the first thing we do is find those asymptotes, and they're talking about check for symmetry and then find any intercepts. So let's go ahead and take a look at those two steps. So if you want to talk about symmetry, for symmetry, remember we replace our x with negative x and see are we having an even or an odd function, and based on that we can decide what kind of symmetry this function will have. So replacing our x with negative x will give us negative x on the top and then negative x minus 2 on the bottom. Obviously we're not going back to the original function because I have a negative x which will stay behind on my numerator, so I don't have an even function. Now the question is, do I have an odd function? And for it to be an odd function, the only difference should be that if I put a negative in front of my function, I should have an odd function, right? But look at this. Even if I put a negative in front of the original function, you can think of that negative going with the numerator, which makes it negative x. But that x on the bottom should still stay positive. And as you can see, that's not the case because I still have a negative x on my denominator, which means I don't even have an even function here. Not odd. And that leads us to the conclusion that we have actually no symmetry. Okay, so there will be no symmetry on this graph. Then we want to check and see if we have any x or y intercepts. So let's start by finding our x-intercepts next, which is where we make our y value 0. Making our y value 0 will basically end up giving us 0 equals x over x minus 2 squared, right? Just replacing the f of x with the 0, keeping our function as it is. And what do you think happens for the x-intercept here? How will I go about solving for it? Yes, Amy?
Multiply both sides by x minus 2 squared.
Yeah, get rid of the denominator. So multiply both sides by x minus 2 quantity squared. And then, of course, on the right-hand side, these guys will cancel each other out. What happens on the left-hand side? 0 times x minus 2 quantity squared?
Yeah.
0 times anything is 0, so you end up getting 0 equals x, which means our x-intercept is at the origin, 0, 0. If we're checking to see for a y-intercept, we make our x value 0. So that would be y equals 0 divided by parentheses 0 minus 2 quantity squared. So what will that give us? What do I get for my denominator? 0 minus 2 quantity squared? 4, yeah, because 0 minus 2 is negative 2. Negative 2 times negative 2 is positive 4. 0 divided by 4 is 0. So again, the origin is our y-intercept, which makes sense because if we got 0, 0 here, we should have received a 0, 0 answer for the y-intercept also. So basically for this example, both our x and y-intercepts are at the same point. All right, so we found our asymptotes, we checked our symmetry, we have found the intercepts, which happens to be the same point. Now they're talking about finding other points to plot and see what kind of shape we get. So let's take a look at what other points we can use. So we have 1.00 from our intercepts. Let's see what other information from our graph do we have. We know there's no symmetry. And let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, now where was our vertical asymptote at? 2. X equals 2. So that would be vertical asymptote right here. Horizontal asymptote at the x-axis, so that's going to be, again, right here. And then we know our x and y intercept is at 0, 0. So let's see if we can find points on either side of our intercept, but also our vertical asymptote. So let's see, how about we do, I don't know, -3, -2, -1, +1. Can't really use 2, so how about 3 and 4 on the positive side? And let's see what kind of y values we can get and how we can use them to graph. So in our function, if we're plugging in our x with -3, what do we get? So that would be -3 divided by, in parentheses, -3 minus 2 quantity squared. Okay, what will we get for -3?
-0.12.
-0.12 as a fraction, that's -3 out of 25, or -0.12. Okay, -2. Yeah. -1/8, which is -0.125. Just slightly bigger than the number we got for -3 at -1. Just 0.1?
Repeating.
Repeating, right? You're not going to get 0.1. You're going to get a repeating 1, 1, 1, 1, 1 because you actually have negative 1/9 here, which ends up giving you a repeating decimal. Okay, add positive 1. One, yeah. Okay, very good. Add 3. 3. And add 4. 1. Okay. Let's see what those points end up looking like on our graph. So we've got, I'm going to start with the nice numbers, 1 and 1. I've got 3 and 3, 4 and 1. So of course you can see this is where we are on either side of our vertical and horizontal asymptote. So this arm of our graph is actually going to come down here and get closer to the x-axis because that's where it's running into the horizontal asymptote. And then this arm will of course get closer and closer to the vertical asymptote and just go up towards positive infinity. Okay, on the left-hand side, let's start by plotting our negative numbers now. So at negative 1, we're at negative 0.11, which literally will be just a hair underneath the x-axis. Then I actually fall a little bit lower because at negative 2, I'm at negative 0.125. So it's actually going to be halfway between a quarter and the 0 on the negative side. So just a little bit lower, and this one's not really letting me do a lot of finer details. At negative 3, we go up a little bit higher. So what should happen here is we should actually dip a little bit and then go towards just a slight dip, because you are going to come down just a little bit, and then of course this arm will go up towards positive infinity. Obviously it's not going to be as prominent as what I drew that, but it should give you an idea of what the function looks like. Let me show you on our graphing calculator here. So this guy was x divided by x minus 2 quadratic squared. Nope. That square has to be on the denominator. There we go. So you should notice just that slight bit of a difference here, and then as it gets closer, as it starts going towards negative numbers on the x-axis, it gets closer to that. So just here, you should see a little bit of a thickness, and it will start narrowing down as it gets closer to the x-axis. So literally just a hair of a difference. Okay, but that's how this function works out to be. Let's see. Can you tell me what the domain of this function is going to be?
Parentheses negative infinity to 2.
Okay, negative infinity to 2.
And then parentheses.
Okay.
And then would it be union 2 parentheses 2 to infinity?
Yeah, so the only number we cannot include in here is the number 2 itself, because that's where our vertical asymptote is, but obviously you can see we're using all the other x values here. Now the range for this will be very interesting because we're not really certain if this is the lowest point on our graph or not, because we really haven't tested any of the other points. There could be decimal numbers in there, which could give us a lower range. And so in this example, we're actually not going to get that minute and talk about the range because it can be a little bit different than what we have on our table. But this still gives you an idea of what this graph in general ends up looking like. Did anybody have questions on this one? Okay, so let's move on to the next one here. Okay, so we are saying the graph of a rational function cannot cross a vertical asymptote, but it can cross a non-vertical asymptote, which means it can cross a horizontal asymptote, it can cross an oblique asymptote, but a graph will, for a rational function, will never cross the vertical. So if you guys actually go back and look at your graph for number 4, right at the middle portion, which was between -3 and +3, our graph actually crossed the x-axis. We had an x-intercept at +1, and of course we had a y-intercept also in this case at 1/9, I think is what it had ended up being. So in this one, you will notice we actually crossed the x-axis. In graph number 5 also, since our x and y intercepts happen to be at 0, 0, we are actually crossing the x-axis and going underneath it, right? So we do end up crossing the x-axis in both these examples. But as we're saying, you will never cross a vertical axis for these graphs, but you can cross non-vertical, so horizontal or oblique asymptote. Alrighty, so as they're saying, for a rational function, the most important feature is its asymptotic behavior. How is it behaving as it gets closer to these asymptotes as it's coming from one side or the other side? All right, let's see what happens with an example like number 6. Now you should notice that the degree of our numerator is larger than the degree of the denominator. So this is an example for oblique asymptote, okay? So let's go ahead and find our vertical asymptote again, and then we'll come back to the oblique. So let's see, this guy is number 6. Okay, f of x equals 3x squared minus 4 over x minus 1. Okay, so vertical asymptote, again, take your denominator, set it equal to 0. What do we get with a vertical? 1. Yeah, x equals 1. Oblique. Now remember, for oblique asymptote, you can use long division. So let's see how long division works out for this guy. We've got x minus 1 as the divisor. We've got 3x squared. You'll notice we're missing the x term, so I'm actually going to leave some space for the x term and then put my minus 4. So just keep a little bit of a blank space for that x term where it should be. Okay, so again, just to refresh your memory, with long division, I have 3x squared with my dividend, and I have only an x in my divisor. So to make this guy into a 3x squared, what do I multiply it with? Yeah, I need a 3x because I have an x, which means I need a 3 and I need one more x. So when we multiply x times 3x, we get 3x squared. And then we multiply -1 with 3x, which will of course make it negative 3x, and you'll see why we left that space open for it. Okay, anytime you are doing long division, you need to change your sign. So the positive will become negative, negative will become positive. Okay, so positive 3x squared, negative 3x squared will cancel each other out, leaving us behind with positive 3x from here and bring down our negative 4. Okay, so now I have a 3x as my term and only an x here. So what should I multiply it with? Yeah, multiply it with positive 3. So that will give us 3 times x, which is 3x. Negative 1 times 3 will be negative 3. Again, change our signs. So this guy becomes negative. This one will become positive. Positive 3x, negative 3x cancel each other out. Negative 4 plus 3, negative 1. Yeah. So this is our remainder. And of course, this is our quotient. So remember, if you're rewriting the original expression, you rewrite it as y equals 3x plus 3, which comes from our quotient part. And then the remainder, you write that as minus 1 over the original divisor, which was x minus 1. Okay? That's just rewriting our expression. As far as the oblique asymptote goes, that's going to be y equals the oblique asymptote only uses the quotient, right? So that's going to be 3x plus 3. Now with this specific example, synthetic division will also work. So if you have, our expression was 3x squared. Again, your x term is missing, so that's a 0. And we had negative 4. Now we're dividing this by x minus 1. So what does our dividend become in a synthetic division? It becomes positive 1 because you take x minus 1, set it equal to 0, which ends up giving you 1. So you are going to be dividing this guy by 1. Okay? Bring the first term down as it is. Then we multiply. 3 times 1 is 3. 0 plus 3 is, of course, 3. 3 times 1 again is 3. Negative 4, positive 3 will give us negative 1. And again, you will notice we got the same remainder as we did with long division. And then our quotient is still going to be y equals 1 degree less than the expression itself. So he becomes 3x plus 3, which also happens to be our oblique asymptote. I will, however, give you one word of caution, because if you notice in your homework, you will see some of these examples are actually given to you as f of x equals, and I'll just use what we're seeing here, except instead of giving you x minus 1, some of those examples are actually giving you just x as the denominator, which means if you try to use synthetic division in this case, since there's really x minus plus 1, none of that, that means you're actually setting your denominator equal to 0 and you're trying to divide by 0. And obviously we know division by 0 is not possible. So in this case, synthetic division will not work. So you have to use long division when they're giving you just an x in the denominator. So just be very, very careful, because this guy will not work, okay? But if you have x minus 1, x plus 2, any of those things in your denominator, then of course synthetic division works out just fine. It's only when you have x in the bottom that we run into problems. Okay, so we found our vertical asymptote, we found our oblique asymptote. Now, does this function have any kind of symmetry? So to check for symmetry, again, replace your x with negative x, which will end up giving us 3 times negative x squared minus 4 divided by negative x minus 1. Okay, so replace your x with negative x. Now on the numerator, since we have negative x to the second power, that's a negative base to an even exponent, which ends up becoming positive. So you will actually go back to 3x squared minus 4 on the top. So that guy actually goes back to being normal. But what happens on the denominator? Will my negative sign disappear on the x? No, because there's no even exponent to get rid of it. So this guy will actually now become negative x minus 1, which means it's definitely not an even function since I didn't go back to the original. However, do I have an odd function? Did I end up getting a negative of the original function? So let's see if we did. So that means if we just put a negative in front of our function, now we know our numerator came out to be the same, right? So I'm actually not going to mess with the numerator. So what happens if I put that negative sign on the denominator? Now what will happen if we distribute that negative sign on the denominator? Negative x plus 1. So did I get this when we check for symmetry? Do I have, bless you, negative x plus 1 on our denominator? We don't, right? We have just negative x, but still a negative 1, which means this guy is not an odd function either. And that means we have no symmetry either. Okay, no symmetry, which means let's move on to finding our x and y intercepts. So do the exact same thing I showed you in example 5, and let me see what x and y intercepts you guys come up with. So what do we get for the y-intercept? The y-intercept, you're making your x value 0, and x-intercept, you are making the y value 0. Okay, so what do we have? You're not going to get a nice and clean answer for the x-intercepts. 0.38. I don't have the decimal approximations, but we can check when we get there. Does anybody have the exact answer for the x-intercepts? Yes.
I think maybe I got x equals plus or minus 2/3.
2/3? Okay, all right, let's check that. So we're setting our y equal to 0. Again, like we did in the previous example, get rid of your denominator first. So we multiply both sides by x minus 1, which of course means on the right-hand side that cancels out. 0 times anything is 0 on the left-hand side. So we end up getting 3x squared minus 4. And our goal is to get x by itself. So here we can start by moving the 4 first. And then divide everything by 3. So Amy, it looks like you should not get 2/3. Okay. So since we have a square on the x, we need to get rid of that square by using square root. And with the square root, we get a positive and a negative root. Of course, these guys cancel each other out. To simplify this, let's actually separate our numerator and denominator into separate radicals. Square root of 4, 2. And of course, we are left behind with square root of 3 on the bottom since we cannot simplify the 3. But this is where the rules of algebra come into play. We cannot leave a radical in the denominator of our fraction, which means we need to rationalize our denominator. And since we're rationalizing a denominator, you have square root of 3 in the denominator. So multiply both the numerator and denominator by that value. And we end up getting 2 times square root of 3 on the top. And what is square root of 3 multiplied by square root of 3 on the denominator? Yeah, it's going to end up becoming 3 because square root of 3 times square root of 3, you can think of that as multiplying into square root of 9, which becomes a 3. Or you can say I am multiplying the same number into itself, so the square and square root can cancel out to give you 3. Either way, you still get the same answer. So this is going to be your x value here. And that means as ordered pairs, we have negative 2 square root of 3 over 3, 0, and positive 2 square root of 3 over 3 as 0. And let's see what those decimal approximations end up looking like. So 2 square root of 3 divided by 3. If your calculators open a parentheses when you type in a square root, make sure you close the parentheses before you divide by 3. Because otherwise your calculator will think you are doing the division inside the radical. So make sure you are closing that. And looks like for this first one, which was positive, I am getting an approximate decimal value of 1.15. And the reason we need decimal approximations is so that we can roughly put them on our graph. And for the negative, well, it should just be negative 1.15. So those decimal approximations are just there to help us graph. As far as the x-intercepts go, it's going to be the exact answers, okay? Oh. Okay, did anybody calculate what the y-intercept was? 4, okay. So let's see, that will be 3 times 0, which is 0 minus 4. And then again, 0 minus 1 on the bottom, which is negative 4 over negative 1, or y equals positive 4 as an ordered pair. That will be 0, 4. So we do have at least one good number to work with. All right, vertical oblique asymptotes are done. We have no symmetry. We found our x and y intercepts. Okay, so let's see what the rough sketch of our graph will look like. we've got 1, 2, 3, 4, 5, 6, 7, 8 maybe. Okay, so let's see, our vertical asymptote was at x equals 1. So positive 1, which will be right here. We had an oblique asymptote. Now this you need to graph like you graph a straight line. So this is y equals 3x plus 3. So for the oblique asymptote, y equals 3x plus 3. Remember, this is our y-intercept. So at 1, 2, 3, 0, 3 is going to be our y-intercept. And then this is a slope of 3 over 1. So you go up 3 and right 1. So use your slope to graph that line. So you're basically graphing a straight line, but instead of drawing this as a solid line, we draw this as a dashed line since it's our oblique asymptote. So let's see, we're going up 3, 1, 2, 3, and right 1. You can also go down 3, so that's 1, 2, 3, and left 1. Oh, and let me see if I can draw this relatively straight. Not really, but you get the idea. Okay, so make sure it's not a solid line when you graph this, because this line is not part of our graph. It's an imaginary line. Okay. Our y-intercept was at 0, 4. So, oh, my line's really off scale here. Okay, let me see if I can draw this asymptote one more time. Okay, after while you're doing that. Okay, and then at 0, 4, we should have our y-intercept, and approximately at positive 1.15 and negative 1.15, we should have our x-intercepts, which means we need to find our points around those values. So we probably want to do, I don't know, negative 4, negative 3, negative 2, and see what kind of points we get for that. Technically, we should be able to use negative 1 in there. We've already got 0, 4 as our y-intercept in there. And then we should be able to do maybe positive 2, positive 3, and positive 4, and see what kind of ordered pairs or points we can get through that. So it's going to be 3 times negative 4 squared minus 4. If you are used to typing all of this in at the same time, make sure you're separating your numerator and denominator by parentheses. Now, if you have those math type calculators, you may be able to type your fractions separately, but if you are working with a calculator that doesn't do that, make sure you're putting parentheses around your numerator and then parentheses around your denominator. So with negative 4, it's going to come out to be negative 8.8. So -4 at -8.8, maybe somewhere over there. -3,
7.75.
7.75. I didn't get that.
I think it's 5.75.
Yeah. So -5.75 at -3 will be 1, 2, 3, 4, 5, 6. Somewhere over there. And hopefully you guys will actually get a better graph than what I have, since my lines didn't come out that nice. Getting about -2.67, and that's an approximate answer, so about -2.67. So -2.67 at -2 will be somewhere over there. And you can kind of see where this graph is heading just by looking at those points. For -1, yeah, 0.5. So -1 is now actually going in here. So this part of your graph, and I'm not sure how well this will show up here. You should be following along this oblique asymptote here on this part. And then on the upper half, you will actually go to the y-intercept, cross that, follow along the oblique. But the moment you hit that vertical asymptote, the direction of your graph will change and it will start going up. So it's basically following along that oblique asymptote, crosses the y-axis, it goes up, but the moment it hits that vertical asymptote, it changes direction and will just start going straight up now. And then for +2, and of course you should be crossing the x-axis there, but my graph is so off at this point. Okay, so for +2, 8. Okay, so that will be 2 and 8. It should be somewhere over there. At +3. Okay. 11.5. Well, I guess that's beyond my scope. And 4.
14.6.
Okay, so that's the part where it's going to keep going up. So this part of our graph is actually going to again follow along the vertical asymptote. It hits the oblique and changes direction. And then this graph, or this part, will actually just follow down on the vertical asymptote. It should really not touch it. But at this point, I've actually given up on my graph. Okay, so let's see, this guy was 3x squared minus 4, x minus 1. 3x squared minus 4. Divided by x minus 1. Okay, so you should kind of see that's the shape of what our graph should take. Now, just to show you what that oblique asymptote looks like, that one was 3x plus 3, and of course that's an imaginary line, but you will notice the more we zoom in, our graphs are not touching those lines, but that's how our graph ends up following that oblique asymptote. But obviously we don't need to draw that line. That's just an imaginary line for us, but you should kind of see that shape where this one here is following along the oblique asymptote and it hits that vertical and starts going up straight. This one here is also going around the oblique asymptote and then it hits that vertical asymptote and just starts going down, but again following that vertical asymptote. Okay, questions on this guy. Yes.
So do you usually like put me in arrangements into like
Yeah, definitely. So any ideas on what that domain should be? So what value of x can we not use? 1. So our domain will be well, if it's not 1, then what is it going to be?
Negative infinity to 1
Mm-hmm.
in parentheses, and then u1 to infinity also in parentheses.
Yeah, so except 1, you can use all values. And basically, if you look at this graph here, this arm, of course, is going towards negative infinity. This arm here goes to, well, it goes here till negative 1.15 or whatever it was, but then it keeps going, and it's using all of these values from 1 to negative infinity on this side. And then, of course, this graph starts at, well, I guess a micro decimal after 1 and then keeps going to positive infinity because this arm will keep going towards positive infinity. Now you can actually talk about the range for this function. So any ideas on what the range, the y values for this function should be? Yeah, you're actually using all y values because both arms of our graph are going up and down, right? So they are going to cover all values because this arm, of course, is going towards positive infinity. This arm is going down to negative infinity. So you are using all y values. Alrighty. Any other questions on number 6? Okay. I'm going to give you guys a couple minutes. Let me see what kind of information you can come up with for number 7. Vertical asymptotes, horizontal or oblique asymptotes, what kind of symmetry it has. Let's get at least those 3 things taken care of, and then we'll discuss the answers. Okay. So if we take our denominator and set it equal to 0. It should have plus or minus 1, right? As far as the domain of this function goes, I cannot use positive 1 or negative 1. So domain will go from negative infinity to negative 1. It will go from negative 1 to positive 1. And it will go from positive 1 to infinity. Okay? But here's the difference in this function that we have not seen any of the other functions. This expression is not given to us in the lowest form because I have x minus 1 on the top, x squared minus 1 on the bottom. So I can factor that denominator into x plus 1, x minus 1. And what that means is that my x minus 1 will cancel out, leaving us behind with 1 over x plus 1. So what happens in this case is we're actually not going to have two vertical asymptotes. As far as our domain goes, yes, we are undefined at two values. I cannot use positive or negative 1 for my domain. But you will actually notice when we graph this function, it only has one vertical asymptote. And that's because the graph was not given to us, or the equation was not given to us in lowest form. And then, of course, we have a horizontal asymptote here. Which in this case, you can take everything and divide it by the highest power of your x. So 1 divided by x, x divided by x, 1 divided by x. So we're just using the simplified version, which tells me these guys are going to 0. He is going to 1, which means you have 0 over 1, which gives you 0. So our x-axis, again, is the horizontal asymptote. Okay, so we're going to have to actually see what happens since I do have a vertical asymptote at -1, but there's no vertical asymptote at +1, and we're saying our domain does not include +1. So we're actually going to have to see how our graph gets affected because of that extra value where our domain is not included. This graph will again have no symmetry because when we put in -x for our x value, we end up getting 1 over -x plus 1. So it's not giving us an odd or an even function here. Okay. I noticed that some of you had started calculating your x and y intercepts. I don't think it should make a difference if you didn't simplify the function. You should still be able to calculate your x and y intercepts. So did we have any answers? Did anybody get those answers or not? Okay, get rid of your denominator again if you're trying to find the x-intercept. So obviously this is a false statement, which means we have no x-intercept on our graph. Okay. If you had not simplified your function and tried to find the x-intercept, you would have got x equals 1. But remember, x equals 1 is where our domain is undefined. So that's why he cannot be our x-intercept, because that's exactly the place where our domain is undefined. Now, if I make my x 0, we should have a y-intercept at 0, 1, which is the same y-intercept you should have gotten if you did the other function also. So like I said, it shouldn't matter. The only thing is we exclude the x-intercept if you did it with the other function because that's where our domain is undefined. Okay, so let's see. What information do we have here? Okay, so our vertical asymptote was at -1. Our horizontal was again at the x-axis. We have no symmetry. We have no x-intercept. We do have a y-intercept at 0, 1. Okay. And I think that's all the information we gathered so far. And we also know that we cannot use, and this is just a note that I'm making for myself, we cannot use 1 either because our domain is undefined at 1. So just something for me to remember. Okay, so let's see what kind of points we can use in our table so we can plot them. Probably do -3 and -2 on the other side of our vertical asymptote. We already know at 0 it's 1, which is where the y-intercept is. Even though I technically cannot use 1, I still need to know where my point is going to be. So this is actually going to be our little special case. And then probably want to know what's happening at +2 and perhaps +3. Okay. If you try to use the original function, you will not be able to use +1 in there because that's where your denominator becomes 0. So I would say again use the simplified version to find your point. So that way you're not running into errors, and that would end up becoming 1 divided by -3 plus 1, which is of course -half. This guy should give us just -1. Let's see if I did 1/2 for this guy, but again, he is part of our special case. At 2, we should have 1/3. And at 3, we should have 1/3. So at -3, we're at -half. -2 is at -1. So this is where your graph will actually go towards the horizontal asymptote here. And it's going to go down towards the vertical asymptote here. Okay. On the other side, we're at 0, 1. 1 is at 0.05. So right here, since this is our special case where our function is undefined, we're actually going to have an open circle at 1 and 0.5 because basically our graph is coming, it's skipping that 1 point, and then it continues forward because since my domain for this function is not defined at 1, you cannot draw a continuous curve through that point. So that's why we put a little open circle, and again, I'm obviously exaggerating my open circle, but make sure you leave an open circle there. Then we're going down to 2 and 1/3, which means I'm getting closer to the x-axis, and I keep getting closer to the x-axis. So this arm, starting at 1, is going to follow along the horizontal asymptote, leaving my open circle at 1.5. This arm again will go up and start follow along the vertical asymptote. Okay. Now the problem with this function is if you graph on a graphing calculator, it does not show you that skip on the +1 where our domain is undefined. So this guy was x minus 1 divided by x squared minus 1. So So you will notice right here at 1.5, it's not really showing you any skips. You will not see some kind of open circle at this point right here, because graphing calculators don't do that, which is the drawback of a graphing calculator. But other than that, you will obviously notice everything else matches the graph that we did, with the exception of that little open circle part. Okay, can you tell me what the domain and range for this function will be? Well, we actually already talked about the domain, so let's talk about the range, because domain we said would go from -infinity to -1. Then it would go from -1 to 1, because I cannot use that little part, and then it goes from 1 to infinity. So just let's rewrite that as we got from the top. -infinity to -1, -1 to 1, 1 to infinity. But what can you say about the range for this function?
Would it be,
Go ahead.
I don't know, because I don't know what happens at that one weird point with the y.
Okay. Let's ignore that part for first. So let's start with -infinity. Where do you go?
-0.
Yeah, you have to go from -infinity to 0, because remember at 0 we have a horizontal asymptote, which means we're not using 0 on the y-axis either. Then we pick up from 0, and where do we go? Same thing, just like we skipped that 1 in our domain, we're actually going to skip that 1/2 in our range. So we're basically saying we go from, not including 0, but we go from 0 to 1/2, but I cannot include that 1/2, because again, that's where my point is skipping. And then I pick up right after the 1/2, and I go all the way to positive infinity. So this guy also breaks up into 3 parts because of the horizontal asymptote, and then not using that 0.5 on the y-axis. So that's where that 1/2 is coming from. Okay. Alrighty, guys. So this was about graphing your rational functions. So after all of that, here's the good news. If you haven't made it to the homework yet, you're not actually graphing these graphs for homework. You're selecting the right graph from 4 different options. So which means as long as you can find the right asymptotes, you can find if there are going to be any skips like this, it will help you determine what your graph should be. And then again, if you calculate your symmetry and y-intercepts, x-intercepts, you will get a better option. So you still have to go through the checklist. You're just not physically doing the graphing for homework in this case. Okay, the next part here is just talking about solving rational inequalities, again, based on graphing or the test point method. You right, see?
Or is it just
You'll again be selecting just a graph, because it takes a long time to graph these by hand, and I don't want you to spend that much time graphing. You'll be graphing for the other ones, just not for this one. Yeah? Okay, so just a little bit of a different method when we are solving these rational inequalities. Of course, the graphing method is going to be pretty similar, but it's going to be the test point method, which is a little bit different. So this one is saying, as long as you have a numerator and denominator with polynomials on top and bottom, we call it a rational inequality, and we'll be solving it again with both graphing and test point method. So this number 8 is actually very similar to what we just did with number 7, where this is not given to us in the simplified form. So the first thing we're actually going to do is again set our domain so we know which values don't work for the domain, and then simplify our function. So pretty much very similar to what we did in number 7, but we're using this to solve our rational inequality. So we are given x minus 2 over x squared minus 4 is greater than 0, and they want us to use a graph to solve this. So let's start talking about the domain first. Take the denominator, set it equal to 0. And at this point, I would assume you guys should be comfortable doing this calculation. So there should be two answers, two values of x that we cannot use for our domain. Okay. But now if you try to simplify this function, or expression, I guess in this case, factor the denominator first. And what does that denominator factor into?
X plus 2x minus 2.
Yeah, x plus 2x minus 2. So the x minus 2 and x minus 2 will cancel each other out, leaving us behind with 1 over x plus 2, which is where we will get our vertical asymptote from. So again, you will see very much similar to the previous example. Again, the degree of my numerator is smaller than the degree of my denominator. I have just 1 on the top, x plus 2 on the bottom, which means our horizontal asymptote is again going to be at the x-axis, y equals 0. So degree of numerator is less than degree of denominator. This function will also have no symmetry because again, if we try to put in negative x for our function, it's not going to work. Yes.
Would we have to write that out if we, so if we were to just put 0, 0?
No, this is just if you guys go back and review the notes, you should know why I didn't spend time doing the whole big calculation.
So just like 0, 0.
So yeah, I mean, that shows me you understand
Okay.
why you're using that. So yeah, you don't have to write it out. Okay, so testing for odd or even function. What did this guy simplify into? X plus 2. So it's not even, it's not odd. That's why it has no symmetry. And remember, we're specifically talking about symmetry with respect to the y-axis or the origin. So if it's not even, not odd, it's not going to have any of those two types of symmetry. Okay. We should have a y-intercept for this guy. And I have a feeling we don't have an x-intercept, but we will go ahead and check for that. So that will be 1 over 0 plus 2, which is 1/2. So that's where the y-intercept is going to be. For x-intercept, we make the y value 0, so that will be 0 equals 1 over x plus 2. When we try to get rid of our denominator, x will basically end up disappearing. We get a false statement, so there's no x-intercept. All of these are literally the same things we saw with the previous example, just our numbers are changing because it's a different function, but all of those same things are repeating. No x-intercept. We have a y-intercept. Only one place where we have the vertical asymptote. We have a horizontal asymptote. And one number is not included in our domain other than the vertical asymptote. So if we put all of this together, our graph should look like, okay, yes.
So all of them have no symmetry so far. When we do get one that does have symmetry, maybe you have to draw a line for it, or how do you represent it in our graph?
What do you mean by line?
Like when it does have, like if it does have even or it does have odd symmetry, do we have to like represent it somehow in our graph, or?
It should show up automatically if your graph has symmetry. So I don't think you need to do anything like extra. It should automatically show up as, if it's with y-axis, then the two halves should look the same. If it's with the origin, then it would actually, if it's at the origin, it would end up looking like a function that is more like 1 over x kind of function. So you would see that. But like I said, you don't have to do anything extra. It should show up automatically. Yeah, as long as your points are correct, it will show up. Yeah. All right, guys. So our vertical asymptote was at -2. X-axis is still the horizontal asymptote. We have y-intercept at 0, 1/2, which will be right here. We have no x-intercepts. We have no symmetry. And just kind of using example 7 as a guideline, this graph is going to again go down this way on the left-hand side. Okay, and again, if you wanted to use ordered pairs, you can, but I'd really like to be able to get to our test point method, and then this graph will go this way. Okay, so very similar to number 7, but our main goal here is to try and see how we can solve the inequality, and the inequality given to us is where is this function greater than 0. So what part of our graph is showing y values that are positive? And again, you should have an open circle right here at +2, because that was not included in our where did it go? Okay, so it should have an open circle at this place, and then it should go up here. So this is strictly greater than 0. What part of our graph is showing y values that are positive? So will this be part of our solution set here? No, because all of these values are below the x-axis, which means all the y values here are going to be negative. So this is not even included. This arm, of course, is going up, which means he has positive y values. This arm is also staying above the x-axis, so this will also be positive y values. And again, we cannot include that 2 in our solution set. So what will that end up looking like, our solution set? Where does this interval begin? It begins at -2, yeah. So for this inequality, we're starting at -2, and how far can we go? We can only go till 2 because I am skipping that little point there, so I need to make sure I stop at 2, and then I can pick up on the other side of 2 and keep going to positive infinity. Okay? So always be mindful of that one place where these functions are going to make that jump, just because our domain would not be at those values. Now with the test point method, again, like I said, it's going to be kind of similar to what we had done with the quadratic and the polynomial inequalities, but our treatment will be a little bit different here. Same thing, we want to make sure we get 0 on one side and our expression on the other side. And you'll notice we do have a 1 on the right-hand side instead of a 0. So that's the first step we start with, is subtracting that 1. Then we take our numerator and denominator separately and find the zeros for both numerators and denominators. One of them will give us the x-intercept. The other one will actually give us the vertical asymptote. So the numerator actually gives us the x-intercept. The denominator gives us the vertical asymptote. And we have to take both of those into consideration. And then from either side, just like we did with other ones, from each interval, we pick our test points and see where our graph is positive or negative. So actually, let's start by cleaning this guy up. So subtract that 1 and bring it to the left-hand side. So if I am subtracting that 1, I should be able to get 0, but that means now I need to clean up this left-hand side because I cannot have plus or minus in there with two different expressions. So rewrite that guy as 1 over 1. We need to find a common denominator. So since this guy is x minus 1, I need to multiply these guys also with x minus 1. Okay. So first fraction stays the same, 1 over x minus 1. These guys here will now become x minus 1 over x minus 1. So using a common denominator, I now have 1 minus x minus 1. Anytime you have a minus sign, make sure you're putting the second expression in parentheses because we need to remember to distribute that negative sign. If we don't, it will completely change the value of our expression, obviously giving us the incorrect answer. So that ends up becoming 1 minus x. And of course, negative times negative becomes positive 1. Same denominator. So that will now become 1 plus 1, which is 2 minus x over x minus 1. Okay. And all of this is greater than equal to 0. So this is what our inequality will look like now after we have put 0 on the other side. Okay. Did you have a question?
No.
Okay. I thought you had raised your hand up. Okay. So 2 minus x over x minus 1, just cleaning up our expression when we subtracted that 1, brought it to the left-hand side. Now the next stage, this is a little bit of a difference from the previous examples we've done. Take both numerator and denominator, set it equal to 0, and find your zeros from the numerator, find the vertical asymptote from the denominator. So let's start with the zeros first. So that's going to be taking the numerator, setting it equal to 0, which will give us, just making my x positive by moving it to the other side, x equals 2, right? We'll get the vertical asymptote from the denominator, so that's x minus 1 equal to 0. Move the 1 to the other side, get x equals 1. So zeros from the numerator, vertical asymptote from the denominator. Now on our number line, we're going to put both of these values. So I've got positive 1, I've got positive 2. And I actually like to write down what number represents what. So I know my vertical asymptote is at 1, and I know my x-intercept is at 2. So that way it makes it easier for us to see how we can write our solution set down. Now pick a test point from each interval. So what can we pick from this interval here? Okay, 0. In the middle? 0.5.
Oh, 1.5.
1.5. And after 2? Sure, 3 works. Okay, so remember, you take your test points and put it back into the expression to check and see do we have a positive or a negative value. So that's going to be this modified function that we're going to be using this time around. So let's start with our test points. X equals 0 will give us 2 minus 0 over 0 minus 1. 2 minus 0 is 2. 0 minus 1 is negative 1. Negative 2. That means we have a negative sign in that interval, right? Okay, when we use x equals 1.5, that will be 2 minus 1.5. And on the denominator, 1.5 minus 1. What does that end up giving us? Yeah, because you will get 0.5 on the top, 0.5 on the bottom. That's half divided by half, which ends up giving you 1. So that's telling us we actually have a positive sign in the middle. And then with x equals 3, negative 1, okay. So that will be 2 minus 3 over 3 minus 1. 2 minus 3 is negative 1. 3 minus 2 is 3 minus 1 is 2. Well, negative 1/2. Okay. Our inequality is 2 minus x over x minus 1 greater than or equal to 0. So greater than or equal to 0 what will be its solution set? So where is it greater than 0 at?
In between 1 and 2.
In between 1 and 2. Where is it equal to 0 at?
At 2.
Yeah, because remember, we have a vertical asymptote at 1, so we can never include the vertical asymptote. So we know between these two values, it's going to stay positive. This is where all my y values are greater than 0. But only the place where I have the x-intercept, it's actually going to equal 0. So your solution set will be between 1 and 2. I cannot include 1 because that's where the vertical asymptote is. But I can include the 2 because that's where it's equal to 0 at. Does that make sense why one gets included and the other does not? No? Why not? What happens at the vertical asymptote when we draw our graph? Come on, we've done multiple graphs at this point. What happens when you have a vertical asymptote to your graph? It's not going to touch the line, right? It either goes up to positive infinity or goes down, or sometimes it can both go up, both go down. So that's the reason why whenever you have a vertical asymptote, you cannot include that as part of your solution set because you have no function at that exact value, because that's where your function is undefined, right? Because that's the number where I cannot have my domain. So that's the same thing that's happening with this example here. Oh, come back. So since I have a vertical asymptote at 1, which means my graph will either be going to positive infinity or negative infinity, I cannot include that.
So how do we tell the difference between the last problem and this one? Are we going to have that on the test?
Possibly.
Possibly. And so how do we...
The only difference between the two is the first one we use the graphing method, this one we're using the test point method. You are welcome to graph this and see what the graph would look like, But this one, of course, is specifically asking us to use the test point method.
Okay, so that will tell us which one.
Yeah, it should tell you which one to use. If it just says solve, then go with whichever one you're comfortable with.
Okay.
Okay? All right, guys, that really just leaves us with the very last example. And if you have questions about that other test point method, you can ask me after class, but I'd really like to talk about this example here really quickly with the application. So this one is talking about how you can actually use those asymptotes to help you solve examples. So we're saying a horizontal asymptote might indicate that the average cost of producing a product is approaching a fixed number in the long run. So we're basically saying we've gotten to the point where our production is now getting to a point where we're actually more efficient because now it's costing us less to produce whatever this product might be. They're saying a vertical asymptote might show that the cost of a project goes up astronomically as a barrier is approached. So the idea is if you think you're going to be approaching that value and your cost is going up really high, then maybe that's something we want to not continue doing because at some point you won't be able to afford these astronomical costs. So just on different bases where your function is going. So this example is again very straightforward. They're saying a truck rents for $100 per day. So that's your base rental fee. And then for each mile, you end up paying 80 cents extra. So $100 plus how many ever miles you drive multiplied with 80 cents. So they're asking us to write a function that gives the average cost per mile for 1 day rental, right? And what happens to the average cost per mile as the miles get very large, as your number of miles increase. So let's start with that first part where they're asking us to write the function. They're telling us it costs us $100 for each day, and we're paying 80 cents for each mile. So any idea what that function might end up looking like? And they're saying write the function as the average cost per mile for 1 day rental.
Would be 100 plus 80 cents X.
Okay, so we're paying 80 cents for each mile. That means we are defining X as the number of miles. Okay, so it's $100 a day plus 80 cents for each mile. And they're telling us to find the function as an average cost per mile. So what additional value do we need here? Average cost based on each mile, right? They're telling us average cost per mile. And then what happens as your number of miles get really, really large? Obviously, in reality, you won't be approaching infinity, but the idea is what would happen if you approached infinity? Will it get really expensive? Yeah. Actually, you'll get a better deal the more you drive. The less you drive, the more expensive this rental will be. The more you drive, you will actually average out. That $100 will get spread out more evenly. Okay, so this is actually basically the idea of finding your horizontal asymptote here, because I have the same degree of X in my numerator and denominator, right? So you can either use that idea of when it's the same degree, it's the ratio of our leading coefficient, which will actually end up becoming 0.80 over 1 as X basically gets really large. Or your other option would be taking each term and dividing it by the highest degree of X. So then this guy would be going to 0. This guy would be at 80 cents. This guy would be at 1. So you end up with 0 plus 80 cents over 1, which actually tells us your average cost per mile is coming out to be 80 cents, which means that additional $100 you paid, like I said, it gets sucked into the number of miles you drive. So if you only drive 10 miles, that means you're still paying that $100, right? But if you did like a cross-country trip, then that $100 is getting sucked in, and you're actually ending up with a better deal. And you know, obviously, you still have the cost of your gas and whatnot that would still be taken into consideration. But this was just to see what happens with your overall cost the more. And you know, this can be, of course, applied to production costs and that sort of thing. Again, if you've ever worked in a situation where you're having to see, you know, we talk about break-even points and when do you make a profit, when do you make a loss. A lot of those calculations are, again, based on this to see at what point will my cost be equal to my revenue, right? And then how much more do I need to go? All right, guys, as I said, if you needed to know how to work on number 10, let me know. I can send you guys something in for Wednesday. We'll be taking our chapter 3 exam, so please make sure you get all of your homework taken care of. I will be on campus